Welcome everyone. Now we're going to discuss how to compute volume of a solid by using the cylindrical shells method. So hopefully you have seen discs or washers method earlier. Now this is going to be slightly different setup, but very simple idea. So hopefully I will be able to help you through this method with two examples. So here are the two examples. Well, this is the first one. We want to find the volume of the solid obtained by rotating the region bounded by this curve, this one, and this one. And we're going to rotate our region about the x-axis. So here's how the picture would look like. So let's suppose this is our xy plane. And we know square root of x would look like this. So we'll start at 0, and then it will curve this way. This is y equals square root of x. And then x equals 1, that's just the vertical line at x equals 1 right here. This is x equals 1. And y equals 0, that is our x-axis. So this is y equals 0. So the region is this. That's the region we're going to revolve about the x-axis. So this is our rotation of axis. That's the indication. Now the idea is to create a cylinder parallel to the rotation of axis. So imagine you have, since our x-axis is the rotation of axis, we're going to be creating cylinders right here parallel to it. So let's suppose I have one cylinder right here, and imagine it's going to be rotating about the x-axis. So I'm not going to draw the 3D image, but just give you an idea how to set this up. So imagine you're creating infinitely many of them starting from here all the way up to here. So that's the intersection that's going to intersect that one. So here's the region of integration. All right, so now imagine this is your arbitrary cylinder in the region. So since it's parallel to the x-axis, we're going to call this some arbitrary y. So when you set up the volume of this solid, it'll be the integral from some a to b 2 pi times the radius of this shell. So we're going to call it shell radius times shell height. So that's how I like to remember this formula, and dA is going to be determined by depending on the shape. Now, since we're doing horizontal cylindrical shells, we're going to be integrating respect to y. So I'm going to pick my dA to be y. Now, also, these limit of integration will also go along the y. So we're going to integrate from here to here. So that would be from 0 to 1. So our limit of integration will also be y equals 0 to y equals 1. And now we're going to go ahead and find these two pieces, shell radius and shell height. So the shell radius is going to be this distance right here. So from here to here, that radius is going to be the shell radius. And that distance is going to be from 0 to some arbitrary y. So it'll just be y minus 0 or just y. So you can think of this is just going to be y times. Now the height. Well, our height is going to be determined by this point to that point. So if you create infinitely many of them, that's what the integration would do for us. So just take one arbitrary, and that's how we're going to generalize it. So this is going to be the height. So it's going to be this curve minus that curve. And this height is going to be determined by left, right. It's going to be determined by right minus left. So the right curve is x equals 1. The left curve is the square root of x. And again, you want to have everything in terms of y. So I'm going to go ahead and solve this for x. So x is equal to y squared. So that height will be y squared. So there you go. This is our shell height. We're going to put that right here. Will be 1 minus y squared. And that's how you set up the integration for the volume of this solid. So our volume is the integral from 0 to 1. 2 pi, we can pull that outside the integration. So let's put that in the front. The radius, that's y. Height is 1 minus y squared dy. Now let's go ahead and distribute the y. So we will have 2 pi, the integral from 0 to 1 of y minus y to the third dy. And now we can use the power rule of integration. This is going to be 2 pi times the integral of y respect to y, that's 1/2 y squared, minus the integral of y to the third, that's 1/4 y to the third. We're going to evaluate from 0 to 1. And we plug in the upper limit of integration. This is 2 pi times 1/2. 1 squared is 1, minus 1 cubed is also 1. So this is 1/4. And the lower limit of integration will give us 0. So I can ignore that. All right, now let's simplify this. This is going to be 2 pi times, so we put these two in the common denominators. So 2 minus 1, that will be 1/4. And this will simplify to pi over 2. So that is the volume of this solid. So here's our next example. We're going to find the volume of the solid bounded by these curves, and we're going to rotate the region about the y-axis. All right, so let's see how this looks like. So again, I'm going to draw the 2D image. You can imagine the 3D, visualize it, or you can just simply put it in a computer and visualize it. So e to the x, we know e to the x would look something like this. So again, the picture is very useful for these questions because it will help you understand how to find the shell radius and shell height if you're using that method. So here's our graph for y equals e to the x, and then y equals e to the negative x. That's just a reflection about the y-axis. So something like that. This is y equals e to the negative x. And x, so this point right here occurs at 0, 1. And x equals 1, that's just the vertical line. Let's suppose this is 1. Again, not drawn to scale. This will be x equal 1. So the region we're looking at is this one. That's our big R, the region R. So this is the region we're going to rotate about the y-axis right here. All right, so if I rotate about the y-axis, since I'm going to use the cylindrical shells method, that is actually the best method in this problem. We're going to create a shell right here in the region. Let's suppose this is our shell. So that means I'm going to draw the parallel to the rotation of axis, drop down an arbitrary point. Since it's dropped along the x-axis, let's call that x. So that means our shell radius will be the distance from the rotation of axis to this arbitrary point x. That will be the shell radius. And then the height is going to be the following. So the height will be from this to that. That will be the height through the top curve minus the bottom curve. So that will be the shell height. So let's go ahead and find that. So the shell radius is going to be, let's see what that is. So it's going to be in 0 to x. So it'll be x minus 0 or just x. Again, that's this distance right here. That's your shell radius. And then the shell height, it's going to be determined by these curves right here. So that is how you're going to determine the height of all of these shells. So the top minus the bottom curve. So again, since it's vertical, we're keeping everything in terms of x because we're going to be integrating respect to dx. So it's going to be top minus the bottom, e to the x minus e to the negative x. That will be the shell height. So the volume, it's going to be the integral going from a to b. So again, we're integrating along the x-axis. So integration is going to start from here, 0, all the way to that 1. So it'll be from 0 to 1, 2 pi times shell radius, that's x, times shell height, that's e to the x minus e to the negative x, dx. Remember, vertical, we integrate respect to x. All right, that's pretty much how you set this up. Now we proceed with the integration. So we're going to go ahead and pull out the 2 pi. So we have 2 pi times the integral from 0 to 1 of x e to the x minus e to the negative x dx. Now this integral is going to be done by parts. So we'll be integrating by parts. So hopefully you have that idea in memory. I'll leave a link in the description box so you to review integration by parts. All right, so we're going to select u and dv from the integrand. So u will be x and dv, it's going to be the exponential e to the x minus e to the negative x dx. So we're going to retrieve the two missing parts. So du will be the derivative of u, that's just dx. V would be the integral of dv. So integral of e to the x, that's e to the x, minus integral of e to the negative x, that's negative e to the negative x. So it's positive e to the negative x. And now we set up the formula for integration by parts. Okay, so our volume is going to be 2 pi times, so we do u times v, so that will be x times e to the x plus e to the negative x minus the integral from 0 to 1. Here we also evaluate from 0 to 1, v du, so that's going to be e to the x plus e to the negative x dx. So we just need to finish up the integration on this piece right here. Okay, so let's go ahead and do this. So this is 2 pi. Now, I'm not going to work on the first piece yet. I'll do them all at once. So we got x times e to the x plus e to the negative x. We're going to evaluate that from 0 to 1. Now, the integral of e to the x, well, we know that's e to the x. So we have e to the x. Then integral of e to the negative x, that's negative e to the negative x. Now we're ready to evaluate everything from 0 to 1. Okay, so not so bad. Now we evaluate, so this is 2 pi. So let's plug in the upper limit of integration for each of these. So we have x replaced with 1 times e to the 1, and then plus e to the negative 1, and then minus 0 times everything. Well, that would be 0. So the first piece is done. Now the second piece, so we get a minus, carry it down, minus, I plug in the upper limit, e to the 1 minus e to the negative 1 minus now 0, e to the 0, and then minus, that'll be plus e to the 0. Okay, now here it looks like these two will cancel each other. And then I also want to distribute this negative out. So this is going to give us 2 pi times e to the 1 is e plus e to the negative 1 is 1 over e. Here I distribute the negative, so that's negative e plus e to the negative 1. All right, again, so I'm going to write this as a 1 over e. And then here, these two will cancel out, but the next two, this one and that one, they will combine. So you will have 2 pi times 2 over e, which is simply 4. So you can write this as 4 pi over e. That's our volume. Or you can also write 4 pi e to the negative 1. Either of these are fine. All right, so there you go, illustration of two different setup using cylindrical shells.